So let's continue with the last presentation. Prior to the coffee break, let me introduce Dr. Alessandro Povera. He's team leader system integration at Metasest System, and he deals there with motorbikes there. I'm a fan of motorbikes. I myself drive a motorbike. I'm interested to hear. So he studied at the University of Udine, bachelor, master, PhD. His fields of work were in the meantime then wireless power transfer, then in current intelligent power conversion, and at the moment then onboard chargers and DC-DC converters, and that's going to be his presentation topic, onboard charger testing for electric vehicles.
Also Vector for the invitation. Okay, this is my presentation divided in 4 steps: introduction, HIL setup, smart charge, and OBC testing. Let's go directly to the introduction. Probably most of all doesn't know Metasystem. Metasystem is a company that since 40 years is working in the automotive business. Initially with 2 business units as safety and security, so it means alarms and parking sensors, and telematics business unit, so it means black boxes, OBD devices, and other telematic units. Most recently, so it means 8 years ago, we started developing also power converters for e-mobility application. We started with the first product. It was a 3.5 kilowatt OBC for a German OEM, and now we are in production with it. It's not a secret that is mounted in the i3 electric vehicle for BMW. And then we develop the next generation. We are also in production in China with an OBC 7 kilowatt OBC. And then we develop more higher power. And up to now we have a 22 kilowatt OBC that we are the first company that has developed a kind of charger in that power density with 800 volt of battery voltage. We are also involved in products with an integrated DC-DC converter to supply the 12 volt network. So an onboard charger is basically an AC-DC power converter. So it charges the HVDC battery of the EV through an AC network. It can be single phase, it can be 3 phase, it can be a double phase like in the NAR market. And nowadays, this is becoming more and more an intelligent product because we have a communication with the network, the AC network, through communication standard like PLC or CAN communication. We have to control and monitor the vehicle plug. So it means pilot, proxy. We have to lock the plug and also control the flap. We have to communicate with the, of course, electric vehicle network through basically mainly with CAN, but we also have to control some car modules through the LIN, and in the latest product we also have to integrate Ethernet communication inside. We have to manage some charging interfaces like the LEDs for the charging. Also pumps or relays. of course, we have to manage both AC and DC charge management, because fast charging with the DC is coming more and more. Let's look at OBC V-cycle. This is the classical V-cycle for an automotive product respecting the ISO 262, starting from the requirement analysis. Most of the cases with the OEMs, there isn't a change with the doors tool, and then there is a step of design of the architecture and the module, and then there is involvement of the function design. Most of the cases, it can be done with MATLAB Simulink, and so with the so-called model in the loop. Going on, there is a code design. We can use tools to auto-generate code, like, for example, target link, and we can do the code testing. Going on the other side of the V-cycle, we have test requirements, and we have to test our product. And in this case, it comes the hardware in the loop testing. We develop a bench fully based on the vector technology. But why we need an hardware in the loop? Because there is a deterministic execution that always produce the same output from a starting condition. We need to have an automation of the process. This can be done using the script, and then this is fully automated. We don't need the human present during the test execution, so we can run tests, for example, during the night. So if we have a sample delivery, then we can run all the tests related to this sample delivery during the night, and the next day we have the results. We can perform, of course, as seen before in the before presentation, regulation, testing, security, and failure test without risk. We need to reduce the time to market, because nowadays the time from the starting of a project like an onboard charger is very fast, because every OEM wants to go to the SOP very fast, and so we have to reduce the time to the market and reduce the working time for testing. And also, we need to ensure a high level of robustness and quality of the process. Let's look inside our use case of the OBC and our solution. Of course, the HIL environment as an HIL bench. There is a device under test. In this case, it's an onboard charger. We have to integrate real actuators, but we have also to integrate some software modules. So it's a kind of mix, hardware in the loop, model in the loop. More in detail, you see here the OBC in the middle of the slide. So we have some power inputs in this case. The HVAC input coming from the main source. We can also use interface an element like a variac to change the amplitude of the voltage and frequency of the mains. And then we have the HVDC output that interfaces an electronic load that emulates the behavior of the battery. And in parallel, we can have also an HVDC power supply if the power has to go to the other direction. Because nowadays, we also need to test bidirectional solutions. And then, of course, we can integrate the LVDC output to emulate the 12-volt battery, but also because in some cases the OBC has a DC-DC converter integrated, so we can exchange power and use an electronic load to sustain this power. Of course, we need also an element like a chiller, because this OBC is water-cooled. So, of course, we can make tests in different cooling temperature conditions. And we have the HIL Hardware-in-the-Loop simulator that interfaces mainly the signal port of the OBC with all the I/O interfaces and communications interfaces. And here we can place, for example, some physical actuators. For example, the motor of the plug lock connection. Or we can decide to simulate the behavior through a MATLAB Simulink model. We have in the network also a power analyzer, because we want to make accurate measurement of the efficiency, because efficiency is really important for this kind of product. Now we can achieve efficiency level like 95%, 96%. And this is how it looks like our solution. This is the rack in our test bench. Of course, this product is tested in Hardware-in-the-Loop bench, but as already said, we also integrate a plant model that can simulate physical elements or dynamics of the vehicle, in some cases the charging station, and all the vehicle networks in one environment. For example, the battery, in most of the cases, the customer doesn't want to, let's say, give us the physical battery to test it. So to accelerate our test and our development, we need to develop a model, or in some cases, this model is provided by the OEM itself. Then we fully made sensor model and also actuators model in Simulink, and then these models are running in the Canoe environment together. And this is the OBC real-time integration of all the elements. For the power, electronic loads and electronic supplies and battery simulator, they communicate with the serial ports or GPIB ports together. They are connected via a LabVIEW process that is integrated in Canoe. Of course, this was done because we already have a LabVIEW interface for all these elements, but the next step is to integrate it in the VT system directly, because it's also easier. So we communicate with all these elements, and then we, of course, have I/O interfaces with the VT system, and we will see later that we have a particular solution for the PLC with the Ethernet. This is how it looks like the Canoe control panel. So with this panel, we can basically monitor all the physical elements in the environment of the charging test case. So you see that we can monitor the electronic loads, we can monitor, we can start the simulation, we can check all the variables in the environment. We can check the plug connection if we have a valid value of the proximity or the pilot line, and we can check real time also the CAN frames that we exchange with the vehicle. So it's a fully integrated solution for the environment of the charging case. Let's talk about the smart charge. The smart charge means that the OBC has to talk with the network, has to exchange data with the network. The easy communication with the network is done through the control pilot line. It's a physical line, 12-volt line, that exchange basic communication with the network. It's basically the maximum value of current that the AC network can support through the duty cycle of the PWM of the control pilot. But nowadays, the standard is evolving very fast, and in the last years there are 3 important standards for the smart charge. The ISO 15118. This standard is for the combo plug and can handle both AC and DC charging. We have the plug and charge function, so you can plug your vehicle to the network, and the charge starts immediately. And there is an exchange, for example, of the certificate, also for the payment of the charge process. And this is done through the power line communication. That is a high-frequency modulation signal over the physical control pilot line. But in other countries, like in Japan, there is another standard, the SPA standard. This is only for DC fast charging, and it uses a private CAN bus in order to communicate with the grid. The China also has another standard, is the GBT standard. The communication norm is the 27930. It's also only for the DC fast charging, and like the SPA is for the private CAN bus. This is our solution to test the PLC and to integrate the PLC. So basically, we use the VT7870 configured as a charging station. Okay, so in this board there is possibility to configure it as a EV or as a charging station. In this case, it's a charging station, and it communicates via the physical control pilot line with this vector module. And then the Ethernet is then connected via CAN case, you see in the picture, in order to sniff the packages and to, let's say, check if the communication is succeeding or not. The proximity line is realized through another module of the VT system, the VT 2004A. That because there was the need to reproduce different proximity line resistant cases, because in the VT7870 there is also a proximity, but is limited in the value of the resistance. And so we had the need to make it via another stimulus module. Of course, during this process, there is no involvement of power conversion, and we can operate also simulating the full range of tolerance of the elements of the communication in order to check the robustness of our process. And this is the Canoe panel to test, to fully test this PLC. And recently, we actually succeeded on this. We went to the customer, and the communication was working. And this is thanks to the opportunity to have this kind of system that can really accelerate the process of integration of our product in the real application. The other case is for the CHAdeMO. This is similar, but the communication is done through a CAN communication bus for the fast charging, and this is, of course, integrated in Canoe like an additional CAN line. The model for the standard is provided by Vector, and so then we can build up a dedicated Canoe panel to test this standard. Of course, the next step will be also to integrate the DC China standard, because nowadays is coming very fast also the DC China case. Okay, so last step it is to let's say see and understand all the elements of the process of OBC testing with the vector solution. We start from technical specification that comes from the OEM. Then the second step is to write the system requirements, so the internal requirements of our component, and these requirements generates the system test specification. Then this test specification is automatically imported in the VTest Studio, so we can have a reference for each then automatic test that is generated in VTest Studio. We can have a fully traceability matrix with the OEM requirement. This is really important to close the loop of this procedure. And then this is working with the VT system in order to let's say implement the real test and give a test report. Yeah. So the activity is like this: defining the test specification. So create an informal description of the test. This is most of the time done in Excel. Then we need to prepare the test hardware. So we have to use the VT system together with our OBC and the network interface. We use an additional PC as the interface and to handle the control panel of the application. And then we need to create an appropriate Canoe environment, so a specific test configuration. So we have to use Canoe and configure the case. Then we have to write the test using, we can use the test automation editor to generate the test. And finally, we execute the test module together VT system and Canoe environment and generate a report of all the tests. As said before, we are able with this solution to close the loop. So import the requirements in VTest Studio, do the test, get the result, and the result are imported back indoors, so we can check which requirements are covered. And that's all.
Recht herzlichen Dank. Oh, bist du da auch?
Thank you so much.
Or do you have translation? No. Okay. Thank you very much for hearing what really happens in the next time with this onboard charger. I have one question. The complete development process. When do you start with developing your tests in the complete process?
Okay, so first of all, when we receive the requirements from the customer, we start developing our component requirements, okay? And in parallel, of course, there is a development and design of the architecture of the product. But when we have the system requirements, we directly go and write the test cases and configure, in the meantime, configure the HIL simulator. Okay.
So you do it in a very early phase of the development process.
Yes.
Okay. Thank you very much. Sind weitere Fragen? Dann hätte ich noch eine, und zwar, sorry, hier. Die 5. Reihe.
Hello, thank you for your presentation. I have a basic question regarding security. You mentioned that you're also doing security tests. What kind of tests are you doing actually, or performing?
Yes, because actually these are more related to specific software tests, because cybersecurity is something that has to be implemented in our product. And the OEM ask to provide. So basically, these are mainly software tests. So they don't involve all the environment and all the components of our hardware-in-the-loop system. So basically, they are treated as normal software tests. In this case, what I presented was more focused on the system integration test, so the test that integrates hardware and software and the environment.
Danke sehr. So, weitere Fragen? Dann würde ich noch gerne eine anführen. In the complete concept, you pointed out that you use a chiller to cool the system.
Yes.
Sure, and you can do some various environments like hot or cool. Do you test what happens if you switch off the chiller?
Yes.
Okay.
Yes. In some cases, yes, because for example, in the end of line phase, you don't want to have also the water connected, because otherwise then you need to prevent that the water when you package the product later. So normally also the OEM doesn't want to have the water during the end of line phase, and so we also test without the cooling. So this is done also stopping basically the chiller.
Okay.
And also in some cases to test, for example, if there is a fault in the cooling system,
exactly,
what happened, and if the product is saved and react very fast.
Yeah. That's the background, the question from customer point of view. I want to know what happens if something is wrong. Thank you. So, Keine weiteren Fragen mehr. Ich sehe schon die Kaffeepause. Thank you very much once more for this really nice speech.